This is part one of your notes. It's part one because I have Zoom calls coming up in about 10 minutes. So I'm making your video into two parts. I am switching up the order of the chapter. Pretty much we started with simplifying polynomials with multiplication, addition, subtraction, and then went with division. Now, the reason why we divide a lot of times with polynomials is so that we can break down our polynomial into factors and we're able to solve or find solutions when our polynomial is equal to 0. We want to find the x values for that. So if you have like a first degree polynomial, you're going to have exactly 1 0. And if you have a second degree polynomial, you'll have 2 zeros. Third degree polynomials will have 3, and fourth degree will have 4. Okay? We didn't discuss what they're going to look like yet. That's the last part of the chapter, their behavior. But I thought I'd stick with the consistency of the factoring and division and work on that. So if I have a first degree polynomial, we know it's going to be linear. If I have a second degree polynomial, you know it's going to be a quadratic. It's going to have a parabola shape. Third degree polynomial, we said it's going to look like that Loch Ness monster. And then fourth degree polynomial, it'll look like a quadratic. There might be lumps and bumps, but it's going to be similar. Okay, and it's going to go in this pattern of one arm up, one arm down, both arms up or both arms down. Okay, rational zero test or rational root test, or rational root theorem, I should say. This test relates to the possible rational roots of a polynomial having integer coefficients, to the leading coefficient and to the constant term of the polynomial. So the rational root test or the rational root theorem, like I said, textbook companies, like they did with synthetic division. It was never really called synthetic division. It was Ruffini's rule, but just for marketing's sake or making it easier, we say rational zero test, but it was rational root theorem. And I believe it was Rene Descartes that was a big part of that, this theorem. So the problem is what happens when you can't factor a polynomial easily? There's no grouping. There's no synthetic division. You know what I mean? The textbook or I did not give you one of the zeros to work with. You were just given this polynomial. What do you think mathematicians did a long time ago to find all the zeros? All right, well, did they graph it in their graphing calculator? Did they go to 2x to the third and they add 3x squared? Oopsies. I mean, in all desperation, this is what you could do. And you'd say, oh, well, I don't know how to factor this, but if I put it in the graphing calculator, I see it maybe goes through -3 and maybe a little bit below 1, but I don't know what that is. Well, you could work with 3 and then keep chipping away. Well, graphing calculators weren't invented until 1985. So mathematicians back in the 1600s, they thought, what can I do? I could try some numbers. I could plug in 1 and see if I get 0, or I could plug in -1 and see if I get 0. And they thought, okay, I can plug every number in, and that may or may not be a good way to figure that out. Well, Rene Descartes realized that if you took a factor of the constant term, 3, and put it over factors of the leading coefficient, 2, and factors of 3 are 3 and 1, and 2 and 1, and the plus minus means a positive or negative, you could get possibilities. It's like when you go into Google and you're trying to hone your search, so you type more keywords or you use quotations. This is called the rational root theorem. So notice it says rational, so this is only to find the rational solutions. So we could have found 3 over 1, 3, or -3. Maybe it's 3 over 2, which is 1.5, or -1.5. Maybe it was 1 over 2, which is 1/2, or -0.5, or maybe it was just 1 or -1. So Rene Descartes said, okay, I'm gonna just use these numbers. One of them should work. Okay, if it does have a rational solution. If it doesn't, then this won't work. Okay, so if we try 3, will it work? Well, we just tried it in our graphing calculator, and obviously 3 doesn't work. So does -3 work? Rene Descartes would have just tried every number. Now, we probably wouldn't have started with -3. We probably would have started with 1 or -1. And let's see. Drop 2, -6, -3, 9, -3. It did work. So one of our factors is x plus 3, and a 0 is -3. Okay, now what's left over is 2x squared minus 3x plus 1. Okay, so can we factor this? Let's try it. You have 3 terms with a plus in the back. That means this has to be minus, minus. Okay, factors of 1 are 1 and 1, and factors of 2 are 2x and 1x. Does this give me this? 2x squared, check. -2x, -1x, yep, it's gonna work. So my remaining factors are 2x minus 1, x minus 1. So my solutions would be x equals 1/2 and x equals 1. To the third power, you should have 3 solutions. So if we didn't have a graphing calculator, what we'd do is the rational zero test, or the rational root theorem, pick a number that works, keep chipping away, and find our remaining factors. Okay, does 1 work? If I put 1 in, we get 2 plus 3, which is 5, plus 3 is 8, minus 8. Yep, it works. Okay, so that is how you find your zeros now if you can't use division given a factor, or you can't factor yourself. So it says, when solving for zeros, polynomial functions complete the following steps. Determine how many zeros the polynomial will have, 3. Use the rational zero test to state the possible rational values, done. Use substitution or synthetic division to test to see if it is 0, done. Once the depressed equation is to the second degree, solve for the remaining zeros using factoring or the quadratic formula. Well, if it wouldn't have been factorable, we would have had to use the quadratic formula. So let's try this again. And then I'll make a part 2 of this video. So here, we know we're gonna have 3 solutions. So then we're probably gonna have 3 factors, we may or may not. So the following possibilities would be factors of 2 over factors of 8. Well, factors of 2 are 2 and 1, and factors of 8 are 8, 4, 2, and 1. Oh boy. So possibilities we would have is 2 over 8, which is a fourth, 2 over 4, which is a half, 2 over 2, which is 1, 2 over 1, which is 2, 1 over 8th, which is an eighth, 1 over 4th, which is a fourth, have it, 1 over 2, which is a half, have it, 1 over 1, which is 1. So one of these should work. If I substitute 1 in, we'll get 8 plus 10, 18. No, that's not gonna work. If I substitute -1 in, will that work? That'll be -8 plus 10, which is 2. 2, no, that's not gonna work. Maybe -2 will work. So we could just do 8, -2, plus 10 times -2 squared. Oh my goodness, I don't like that. 8 times -2 cubed, bring it down, plus 10 times -2 squared minus 11x plus 2. Well, x is going to be -2, sorry. Yep, -2 works. So if -2 works, x plus 2 is a factor. Okay, so what we're going to do is put -2 in our box, 8, 10, -11, 2. We drop the 8, multiply by -2. We drop the -6 to get a positive 12, which is 1, -2, 0. All right, we've chipped it away. So now we're left with 8x squared minus 6x plus 1. We should be able to factor that. You have 3 terms with a plus in the back. Therefore, this sign is going to appear twice. Your factors are 1 and 1. So is it going to be 4x and a 2x? Or is it going to be 8x and a 1x? 8x squared, -4x, -2x, yep. So there's our factors. And my solution is a fourth, and my other solution is 1/2. All right, I'm gonna come back with part 2 in a minute.